These notes are about standard 2.2, which includes using slope and area on constant acceleration graphs. So the first thing that we need to understand about velocity time graphs is the meaning of the slope on these graphs. And here at the bottom it says that the slope of these graphs represents the acceleration of an object. And so if you were given the graph shown on the left and asked for the acceleration, we would have to find the slope of that velocity time graph. And so in order to do that, we need to find 2 points on this line. The endpoints will work just fine. And then we can find the difference in velocities and divide by the difference in times to get a total slope, which we could write like this. So the total slope here is positive 0.4. And then notice the units, we have meters per second on the top and seconds on the bottom, which we combine into meters per second squared because we're dividing by seconds twice. In order to draw a quantitative acceleration time graph, we can use the slope that we just calculated, and what we can do is we can apply that to the acceleration time graph in a similar way to how we drew velocity time graphs in Unit 1. So by finding the slope of positive 0.4, we can find where that 0.4 is on the acceleration time axis, which is right here, and then we can extend a horizontal line from that acceleration for as long as this slope is exhibited. So this is the same slope for the entire 5 seconds, and so we will extend that horizontal line at positive 0.4 meters per second squared for 5 seconds long. If we have a little bit more complicated of a velocity time graph that shows multiple types of velocities or multiple segments, then what we have to do is we have to look at each segment individually. And so in this graph, it would be good to look at the first 3 seconds on the velocity time graph down here, and then investigate the last 2 seconds separately because they have different slopes. And so if we calculate the slope for the blue line for the first 3 seconds, we find that the slope is 0 meters per second squared. And it is that slope of 0 meters per second squared from 0 seconds to 3 seconds. And so on our acceleration time graph, we can draw at the acceleration of 0, and then for our time duration, it starts at 0 seconds and it goes to 3 seconds. Then we can repeat the process for the red segment on the velocity time graph. We can find that that acceleration is a positive 2 meters per second squared using the slope equation. And so we're going to have a line somewhere on the positive 2 meters per second squared line, but the duration is from 3 seconds here to 5 seconds here. And so that's going to look like this. In order to find the average acceleration on a velocity time graph, we're not going to be looking at individual slopes, but instead we're going to look at the entire time period that they ask us to look at. The equation to find the average acceleration is this one. Average acceleration is equal to the change in velocity over change in time. And if we split up the change in velocity and the change in time into the difference between the initial velocity and the final velocity, or the difference between the initial time and the final time, then this should start to remind you of that slope equation. But notice that we're not going to look at this slope and this slope. We're going to look at the initial time and initial velocity and the final time and final velocity. And so the 2 points that we're going to find in this the 2 points we're going to use in this acceleration equation are just the final and the initial. So mathematically, that looks like this. Final velocity of positive 2 meters per second, and an initial of negative 2 meters per second, and then a final time of 5 seconds and an initial time of 0 seconds. We get positive 4 over 5, and so the decimal form of that would be positive 0.8 meters per second squared. And again, this is the average acceleration over the entire 5 seconds shown in this graph, and so that would be like a slope of a line that connected these 2 red points directly. And we don't have to worry that there are 2 different segments here. In finding a displacement on a velocity time graph, our idea is exactly the same as the first unit. On the bottom here, it says that the area under the velocity time graph represents the displacement. But what's different now is that because our velocity time graphs aren't always horizontal, then our area formula has to change slightly. So if we agree that the displacement is the area, the shape under the curve is now a triangle. And so our area equation is 1/2 times base times height instead of just base times height. And so for this triangle, it is 1/2 times 5 seconds, because 5 seconds is the base of the triangle, and then 2 meters per second is the height of the triangle. And if we multiply these together, we get a positive 5 meters or 5 meters to the right. And so this shaded area here tells us that during this time period, the object moves 5 meters to the right. If we have a more complex shape, then our understanding of under the curve becomes a little bit more complicated. So you can see down here I said that under the curve really means between the graph and the time axis. And so if we look at this shape, this shaded region is between the graph and the time axis. And then up here, when it passes the time axis, now we're shading under it again. When you have a pretty complex shape like this, it's good to break it apart into rectangles and triangles like this. And then we can find the area of each shape separately and then add them together. So here are the calculations for each shape. Notice that the red shape is a rectangle, and so the displacement or the area equation is just base times height. It doesn't include that half. Whereas the blue and green regions are triangles, and so their equations have 1/2 times base times height. So the red rectangle has an area of -6 meters. The blue triangle has an area of -1 meter. And then the green triangle has an area of +1 meter. And remember, just like last unit, we can be comfortable with negative areas on these graphs because that negativity just communicates the direction of the object's displacement for that time period. So if we're looking for the total displacement of this object based on this graph, we can simply add up those 3 displacements and get a total of -6 or 6 meters to the left. In order to find the distance on a velocity time graph, we're going to do all of the work that was shown on the last slide, but then what we're going to do is just take the absolute value of each chunk of motion and then find the sum of those absolute values. So what that looks like here is taking the absolute value of the red rectangle, the blue triangle, and the green triangle. If we add those all together, or if we take the absolute value, first, we get just positive values, and then we can add them up for a total distance traveled of 8 meters. And notice that there's no direction given on this distance because distances are scalar. And so if you include a direction, that will show us incomplete understanding. Thank you very much for watching.